Hey you guys, welcome back. So we are at almost the last lesson for the summer term of Adult Basic Education Math. And we're going to wrap up this topic, which we started last week. There's a whole lot of things happening in this particular topic, and so I spent the entire last lecture last week going over the angle pairs. So that is done. We did that already. Today we're going to be talking about circles, the parts of a circle, and how you calculate certain dimensions of a circle. We're going to talk about the Pythagorean Theorem, and then we're also going to talk about congruence and similarity of shapes. And before I get any further into this, I did email everybody today individually at your personal email addresses. Because I'm trying to get people together who are interested in continuing with the course in the fall term. There is a break between the summer and fall terms that lasts about a month. And so if you don't register for fall before the end of the summer term, then you're going to lose access to things like Essential Ed and these videos and so on. And so if you're going to continue with the class, I would recommend that you get in touch with me so I can give you the directions to register. I will have the rest of the information starting tomorrow, which is Tuesday the 7th, and I will disseminate that to you guys as soon as I have it. So without further ado, let's go ahead and attack this monkey here. So the first thing is about circles. So we kind of all have a general idea of what the shape of a circle is. It's circular in shape. There's different parts of the circle that we're going to be talking about today. Some of them are labeled here. Every circle has a center. That point is exactly in the exact middle of the shape of the circle. There is a measurement called the radius, which goes from the center and then it's directly straight out to the edge of the circle. Now you can have that radius be anywhere you want from the center out. It could be here to here, or it could be here to here, it could be here to here. All of these individually are called a radius. But the thing they have in common is the length. So however long this radius is, all of these other radii are, and that's how you say it, plural is radii. All of these other radius figures are the same measurement. They're the same length. No matter where you go, it's from the center out to the edge of the circle. There's another measurement inside of the circle called the diameter. The diameter is not printed on this figure, so we're going to go ahead and add it. If you were to draw a line from one side of the circle to the other and it goes through the center like this, that is called a diameter. So I'm going to draw an arrow here and I'm going to call this a diameter. The diameter has to touch both sides of the circle and has to go through the center. And just like the radius, there are an infinite number of diameters inside of this circle. For example, you could draw one right here, and that's also a diameter. It's the same length as the other one. They have the same dimensions to them, the same measurement. But anywhere you draw one, it is considered a diameter. So that's kind of it for the basic pieces or parts of a circle. There are some measurements that we're going to be talking about next, which is the area and the circumference. If you remember, I'm going to go ahead and draw a picture for this. If you go rewind a little and go back to some of our previous lessons when we were talking about quadrilaterals or shapes that have four sides, you would have something like, let's say, like this. That's a rectangle. Okay, it's not a perfect rectangle, but whatever. You'd have a length over here, you'd have a length over here. This should be the same as this one, or you could have like a trapezoid like this, or a rhombus, where you have like these two are the same distance and these two are the same distance right here. You could really easily find the perimeter of a shape like this by basically taking a walk around the outside and just counting up how far you walked. okay, and that would be the lengths of all those sides added together. You can't really do that with a circle, so it's extremely difficult, and the reason for that is because on a circle, there I'm going to tell you something that is not actually mathematically true. If you zoomed in close enough on this circle, if I zoom, there really are very small little, it's almost like stairs. Like it goes like this. Wait, that's not, let me draw this. It goes like this, then this, then this, then this, and this. And that's how you get the shape of a circle. But for practical reasons, there are no straight edges or anything that you can easily measure around the outside of a circle. You couldn't take a ruler to the circle because the ruler, let's say for example you put the ruler up here, well the ruler is straight, okay? The ruler would go like this, and you could only measure that one little point, however long that is, and then you'd have to turn the ruler and measure it like this, and turn it again and measure it like this. And there's actually some stuff in higher math where you would do something like this, a procedure like this in calculus to get, to derive the circumference, but we're totally not there. So what we're actually going to do is we're going to use the absolute closest approximation to finding the circumference, which is a formula that we're going to go over in just a minute. And it uses the radius and the diameter, and it uses a special symbol or a special mathematical number called pi. So we're going to talk about what pi is in a moment, and then we're going to start applying it. The same thing is true for the area. If you were talking about something like a square like this, you would just take the length times the width, and that would give you all the area on the inside, right? That's really simple. But there isn't really such thing as like a length and a width for a circle, and so you have to use a special formula using the different parts of the circle to figure out what the area and the circumference are. So let's talk a little bit about what pi is. So pi is a special number in mathematics. It actually comes from the circle, but we use pi in a lot of different other contexts in math as well. So the question is, you've probably heard of pi before. A lot of people joke about pi. The first three digits of pi are 3.14, and so on March 14th, like the date of 3/14, like this, we usually celebrate Pi Day, and that's just a play on the whole pie thing right here, and people eat pie and stuff. Like last year on Pi Day, I brought a whole bunch of pies into my students, and we had pie on Pi Day. So what pi actually is it is a mathematical constant. It stands for a number, okay? So in every formula that we do, we use pi in, right? Like you could write out 3.14159 and then all the rest of the digits of pi, right? And it would never end because pi is an irrational number. It never ends. That decimal just goes on and on and on and on and on. So even if you approximated pi to 3.14159, if you had to write that over and over and over and over again in formulas, that would be really annoying. And so what you can actually do is just use the Greek letter right here, which is pi, in its place. So anytime you see this Greek letter, it's really 3.14159 dot 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 dot, and then all the rest of the digits of pi. And a cool thing to note is that they're actually on most, at least on scientific calculators, there is a button that stands for pi. For example, here is a common scientific calculator. Let me turn my light on so you can see that a little better. So here's a scientific calculator, a common one, and my pi button is right here. So if I were to punch that in, see how I get pi on my screen, 3.14159, 2654, blah, 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 blah. And if I use the pi button, it's going to give me the closest answer possible because the calculator is taking all of these digits into account. Whereas if you just put 3.14, that's not going to be as accurate as if you use the symbol and do the entire calculation. So we will move that calculator out of the way. Let's see. Usually when you apply pi in a formula, like you're calculating something with pi, wherever you apply the pi, you'll use the pi button. It will give you a really super long answer because the calculator is trying to be as accurate as possible. But on your answer to your question, you probably are going to end up rounding. And this is where, if you remember from the rounding lesson from a long time ago, I kind of gave you guys a little bit of a caution about just rounding everything. If you have a problem, right, and like step one of the problem has like some calculations, this times this, right, and then you get an answer, and you have to use this answer in step two, right? Like you simplified something, and now you're using this answer, and you're multiplying that times something else, right? You're going to get another answer, okay? And then there might be like step 3 and step 4 and blah, 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 blah. And then your final answer that the question is asking you for is something you arrive at after all these steps, okay? If you round all the answers that you get along the way, then your final answer is going to be pretty far from what it actually should be. Like you could literally end up being, a couple of whole numbers off from where you need to be because of improper rounding. Whenever possible, you want to leave these like intermediate answers, the ones you're finding like along the way, along the path. You want to leave them as close to their true answers as possible, including all the decimal points. You really don't want to round until you get to the end of your problem. And that's, we round at the end because if I go through all of this work to get the closest answer I can find, then I can round it a little because my answer is still going to be pretty close to what the true answer is. But if you round all along the way, then you could really be in serious trouble and not get the correct answers. So just be careful with rounding. Another thing about pi, so if you look at this symbol, right, I'm going to just kind of remove all this here about the final answer and the rounding and stuff. If you look at this symbol right here, okay, or this figure, I should say, you have a circle, the diameter goes across and touches both sides through the center, right? That's what we talked about before. The radius is just half of that. It comes from the center and hits the outside. The circumference is the measurement of the whole circle. And if you take the circumference, whatever that value is, and you divide it by the diameter, you will always get pi. And that's true for any size circle. So if I drew a circle that was this small, or a circle that was this large, or a circle that was this large, if I divided the circumference divided by the diameter, I'm always going to get pi as my answer because pi is a ratio of the circumference and the diameter of a circle. That's where the number is derived from, okay? All right, so let's talk about circumference. The formula to find circumference, let's highlight that, okay? The formula for circumference is that capital C, that means circumference, is equal to the Greek letter pi, the mathematical constant pi, times the diameter, okay? You might also see sometimes the formula might also be written, how about orange? Well, let's do markup as orange, okay? You might also see the formula written in this way, which is C equals 2 pi times r. And all this is saying is that if I go off on the side here, thus the diameter of a circle is double the radius, right? We know that to be true. Let's go back to our figure. The diameter is just double whatever the radius is. So anytime I see the diameter, I can swap that for 2 of the radius, okay? And that's really what's happening here. If you look at the things that are the same in these two formulas, let's cross them out. C equals, okay, so we have a C equals on both of them. Let's cross that out. We have a pi on both of them, right? So get rid of the pi. And all you have left is D and 2r. Well, we know that D is the same thing as saying 2r. And that's why these formulas are really interchangeable. Do I have an undo function on here? Let's see. Yep. I just don't want to erase the highlighting. I want to get rid of the lines. Okay, there we go. So keep that in mind. The circumference can be either found by taking the diameter and multiplying it by pi, or taking 2 of the radius measurements, whatever that comes out to, and then multiplying that times pi. The other formula that you're going to need to know is how to find the area of the triangle. And so what happens here is that you're going to take the formula is A equals, and then the Greek letter pi times the radius squared. Now you technically could replace the radius here with a d for diameter. It is, let's talk about what that proportion is, right? So like the radius is the diameter cut in half. Like here's my circle and here's my diameter. Well, if I just wanted the radius, okay, that would be just this half right here, okay? So the radius is half the diameter. So anytime you see an r, you can swap that for a d divided by 2 or a 1/2 of d. That's less common. You probably won't see that. Most of the time you're going to be given the radius, not the diameter. So just keep that in mind. And those are your formulas. So let's do some problems where we are applying this information. Here we have some practice problems where we are going to calculate the area and the circumference. The directions say find the area. Whoops, we zoomed in a little, sorry. The directions say find the area and the circumference of each circle with the information that you are given. So in the first problem, I'm gonna do this one, and then you can go ahead and pause and do number 2. The radius on this one, that's this leg right here, this piece from the center to the outside, this is a radius. The radius is 12, so r equals 12. And then since I have the radius, to find the circumference, I'm going to use the c equals 2 pi r, okay? So 2 times pi times 12. Notice how where the r was, I've now written 12 because I know what the radius is, okay? I don't know what the circumference is. That's the only thing that I'm solving for, or the only thing that's missing here. Let's go ahead and do that calculation. I'm going to use my calculator for this, and I probably need to turn my light on. Let's do that. Okay, so to find the circumference, I'm going to do 2 times 12 first. Remember, multiplication is commutative. So this right here, you can do this in any order because the only operation you're doing is multiplication. You can do 12 times 2 and then times pi. You can do 2 times pi and then times 12. You can do pi times 12 and then times 2. Whatever you want. I think it's easier to just get rid of that. So this is telling me that c equals 24 times pi. And be careful here because your question might ask you to just tell me in terms of pi what the circumference is, and you would stop here, okay? But if it wants like an exact measurement, you're going to take 24 and hit multiply and then hit pi and then hit equals. And so now I can see that my circumference is 75, and I'm going to round this figure. I want to round it up 1. So this is 75.4. I'm just going to take it to the 10th place, okay? And don't forget that they gave me the dimension, which is in inches, okay? Or the unit, rather. So the other thing we need to do is calculate the area. How about blue for that? The area of a circle is pi times the radius squared, okay? So to find this out, you're going to take 12, and I have a button on my calculator right here that says, you can't see that, let me roll that up. I have a button right here that says x squared. This is going to take whatever you typed on the screen here, and it's going to square it. So it's a shortcut. You could also just do 12 times 12. It's going to give you the same answer, okay? So I know that's 144. And your problem might say, hey, in terms of pi, what's the area? Well, it's going to be 144 pi inches squared, okay? Why am I doing inches squared? Okay, so remember, go back a little bit to the measurements lesson for the quadrilaterals, okay? Anytime we talked about the area of something, that is a two-dimensional construct. So that's going to have an exponent here of squared because that's telling me that it is two dimensions. And remember, we also talked about the volume of some figures also. That's three-dimensional figures have volume, okay? And so if there's a volume, the volume is going to be with an exponent of 3. And that tells me that the measurement I'm looking at is a three-dimensional measurement, okay? Keep that in mind. Now, your problem might want an exact answer, okay? And so what they mean is take 144, multiply it times pi, and then that's going to be whatever that is times inches squared. So it's going to be, I'm going to take it to the 10th place again. That's 452.4 inches squared. So 452.4 inches squared. Okay, so go ahead and pause the video. Let me turn my light off here. Pause the video and go ahead and work on the second question. You have the radius and you need to find the area and the circumference. Okay, so this is what you should have gotten for the circumference and the area of this circle. And I want you to go ahead and also do the practice problem that is under number 3. And go ahead and also try number 4. We're going to pause the video. When you unpause, I'm going to have the answer here for number 3, but I'm going to do number 4 with you and step you through it. So go ahead and pause the video again and do number 3. Okay, so here's your answers for number 3. The challenge here was that you were given the diameter this time, not the radius. And so if you tried to visualize that on a circle, right, like you were given this measurement the whole way across. And for the formulas that we've been doing, you kind of need like the radius, which is just half of that. So you would have had to, circumference is not bad because if you remember, the circumference is just the pi times the diameter. So if you have the diameter, that's easy. But the area formula, you would have had to first find what is the radius, right? What's half of that diameter, and then square that number. And so if you forgot that step, then here you go. We took half of that first and got 34.1 for the radius, and then squared it, and then multiplied that by pi. Okay, the challenge question on number 4, if the circumference is 32 meters, what is the diameter? Well, this is just like any other formula, and so you just need to sort of like sort of backwards engineer it. Like in this situation, you have the final answer already, so to speak. Like you already know, what the outside of the circle measures. You have the circumference already. What you're looking for is the diameter. You want to know what's that piece in orange, right? That's what they're asking you for. So if we use the formula C equals pi times the diameter, right? I chose this because I'm going to be able to fill in the C, and then I'm just going to have to solve for D, whatever D is. That's going to give me the diameter. So the whole answer of the total is 32 meters equals pi times diameter. So let me ask you a question now. How many unknowns are there in this problem? There's only one. It's only this D right here that stands for diameter. This M is not a variable. This just means meters, okay? Because they gave you the problem in meters, all right? So to get this solved for, I need to divide both sides by pi. What that does is it cancels out the pi over here. And now I have this D, letter D, all by itself. So 32 meters divided by pi is going to give me the diameter. So all I really need to do is just do 32 divided by pi, and I'll have my answer in meters. 32 divided by pi. So the diameter is 10.2 approximately meters. And that's it. That's your challenge question. Okay, I have an additional video for you on this if you need a little bit of extra help or brushing up on parts of a circle and how to do like what pi is and all that stuff. It's right here in this document. If you pull up this document on Google Classroom, you'll be able to just click right on it and it'll take you to the video. So keep that in mind. We've got the Pythagorean Theorem to talk about still, which is about triangles, and then we're just going to talk about congruence and similarity. If you need to, like, grab a drink or use the restroom or something, pause the video. Go ahead and do that now before we delve into this next topic. Okay, so our Pythagorean Theorem, right? Like, that is a huge word, Pythagorean Theorem. What even is that? Why can't we just call things like they are? Well, Pythagorean Theorem gets its name because it was discovered by a Greek thinker back in ancient Greek times named Pythagoras. That's the only reason it's named that way. If you look around our world today, there's plenty of things that are named after the people who invented them. So just keep that in mind. Like, that's where this word comes from. All right. It also, I think, is kind of helpful that it has kind of a funky name because, like, it makes it easier for you to remember and differentiate it from other things. So what the Pythagorean Theorem says is that whenever you have a right triangle, and we're going to refresh ourselves on what that means, there is a special relationship that exists between the sides of that triangle that puts them in a very particular proportion. And so this is very handy for lots of reasons in trigonometry and calculus, but for our purposes, we're going to use it because it's going to help us find a missing side of a triangle when we're given the other two. That's the type of problems that you're going to see, and that's what we're going to focus on here. So let's remember that a right triangle is any triangle that has a 90-degree angle. And a 90-degree angle is denoted by this little box in the corner right here. This top one is not a 90-degree angle. There's no way. And this is also not a 90-degree angle. And on this triangle, you have three sides, A, B, and C. Those are the side lengths. Okay, we don't know what these particular ones are, but what we know is that if you square this side and you square this side and add them together, you're going to get whatever this side squared is. That's the relationship. That is what the Pythagorean Theorem tells you. That is the thing that you need to memorize. Memorize. Okay, memorize this. It's very important. A squared plus B squared equals C squared. You're going to use it in so many things in higher level math. Okay, one more note is that if you remember from our definition of the parts of a triangle, on a right triangle, the longest side is called the hypotenuse. Hypotenuse, that's how you pronounce that, hypotenuse. Okay, and so with the Pythagorean Theorem, we usually always use the letter C to refer to that long side, the hypotenuse. So another way to think about this, like for some reason, let's say you were given a right triangle that was like this, right? It's like X, Y, and Z. Well, this, X, Y, and Z, you're like looking at this formula for A squared plus B squared equals C squared, and you're like, I can't do it because there's no A, B, and C here. Well, hold on, because you definitely can do it, okay? What the Pythagorean Theorem is telling you is that the first short side squared plus the second short side squared is equal to the hypotenuse squared. That is what the Pythagorean Theorem is telling you. Figure out what are the two short sides and figure out which one is the longest side, and that's how you're going to be able to apply this in any situation. Oh, my next page here is not loading. So hold on one second while I reload my document here. One moment. Oh wait, I think I just opened last week's notes. Whoops. Nope. Hold on. There's last week's notes. One second, you guys. We're just gonna reload this page and get my extra page here. Okay, all my notes are there. Okay, perfect. So we're going to do some practice problems using the Pythagorean Theorem. Notice how none of these are labeled with A, B, and C, so you're going to have to figure out what are the short sides and what is the long side. Another way to remember which one is the long side is the hypotenuse is always across from the right angle. Okay, so hypotenuse is always across from the 90-degree or the right angle. Okay, that is always 100% of the time true, and so in all of these right now you should be able to figure out by using that rule which sides are the hypotenuses on these problems. Okay, so let's do the first one together. We're solving for the hypotenuse, so we're going to call this C. And you can call this one A and this one B if you want, or you can call this one B and this one A if you want. They're interchangeable. It doesn't matter as long as you're using them in the same order every time. So let's say that A is 4 and B is 8. So what does C come out to? Well, using the Pythagorean theorem, we know that A squared plus B squared equals C squared. And so 4 times 4 is 16. 8 times 8 is 64. Okay, keep calculating here. 64 and 16 is 80. So 80 is C squared. Now this is where a lot of people get tripped up with Pythagorean theorem problems because they think that they're done because they've found the answer. Well, all you've really discovered here is you've discovered that that C squared comes out to 80. Okay, that's all that you have figured out, is that C squared is 80. You don't know what C is. You don't know what this side length is. You just know that whatever the length is squared comes out to 80. So you have to do a certain operation here that is the opposite of this squared right here. You have to do the opposite of that, and hopefully you're thinking and searching your brain and figuring out what is the opposite of taking a square of something. We covered it recently. So the opposite of squaring something is taking a square root. So you're going to take the square root of this side and take the square root of this side. Okay? And what you've done essentially is you've gotten the C by itself, which is your goal. That's what you're looking for, right? You want to find C, not C squared. And on the other side, you have a square root 80. Now, there's a whole mathematical thing we can do where we look for, how to simplify that and leave it in terms of a radical with a square root. We're not going to do that. We're going to actually just approximate what the measure comes out to. So if we just figure out in our calculator, if we put in 80 and then we take the square root of that, we get 8.94. I'm okay leaving that as like 8.9. That would be sufficient, I think. So C is going to be approximately 8.9. All right, and so you have found the missing side length. And that's really all there is to it with these Pythagorean theorem problems, at least the ones that we're going to be covering. So I'm going to leave the other 3 up to you right now to give those a try. It would be super if you would just pause the video and take a couple of minutes and do all of them. Don't just do 1 or 2. Like, just do all 3 of them, and then when you come back, the answers will be displayed on the screen. So I'm going to wait a minute before I pause my recording here. So you can have a chance to pause your video. Go ahead and pause it. Okay, so the answers are all displayed here. I just punched them in my calculator to calculate them. You were solving for the hypotenuse in all of these problems, okay? And that's it. I mean, you might occasionally come across a problem where you have to find a different side That's totally possible. Just make sure that you do this part right here where you define what all the sides are and say what their measurements are, and then plug them in accordingly to your equation, which is a squared plus b squared equals c squared. Okay. And then you should be able to solve any one of these right triangles and get those missing sides. Okay, so that is actually all we're doing for the Pythagorean theorem. So we've covered 2 out of our 3 topics for this lesson. We've talked about the parts of a circle, how to find the area and circumference of a circle. We've also talked about the Pythagorean theorem and how you can use that to solve for a missing side of a right triangle. The last thing we're going to talk about is congruence and similarity of geometric figures. So let's talk about congruence first. When you see the word congruent, that means that 2 shapes have the exact same size, dimensions, measurements. They're identical, okay? They are completely the same shape, but you might see them like, flipped upside down or turned in a different direction. And so like when you look at the shapes right away, it might not be immediately apparent to you that they're identical, but once you lay them on top of each other, you can see that they are congruent. Think about when you go to the store and buy a pack of paper plates or napkins, okay? Typically you get 30 paper plates in a package, or if you go to Costco, it might be 100, in a package. All of those paper plates stack so nice and neatly with each other because the shapes are congruent. They are the same size every time, okay? And the same thing is true of the napkins. And when you see the napkins, right, let's say you take those napkins out of the bag and you put one napkin down like this, okay, that's a napkin, and then you put another napkin down slightly sideways, right? Well, you might be looking at me right now and thinking, well, this is a square and a diamond, so they can't be congruent. They totally are if you just turn this shape. I wonder if I can actually do that on here. Let's see. No, I can't turn it. Okay, well, I tried. But if you turn the diamond a little bit this direction, it'll fit congruent, identical with the square. And the same thing is true the other way. If you turn the square a little bit to the side, it would be congruent with the diamond. Okay. So let's do some practice. Here's a little, this is a clip it from a worksheet. The 2 first shapes are definitely congruent. They look exactly the same to me. They're going to fit right on top of each other. The second ones, they are congruent. They're just facing different directions. Like one was transformed and turned around. So it doesn't look immediately like they're congruent. But if you took this one and here's the palm of my hand. If I take this shape and I flip it over like this, like I'm flipping a pancake or flipping a burger, right? They're going to fit right on top of each other and they are going to be congruent, okay? The last 2 shapes here, not congruent, and it's very obvious to see why they're not congruent because this one is smaller in dimensions than this one is. So go ahead and tell me your best guesses for A, B, and C. Just go ahead and write them down. You're going to just tell me if they're congruent or not congruent. I'll give you a few seconds to think about that and write it down. Okay, awesome. So on the first one, they are congruent, right? Whoops, that's not the drawing. Check mark. They are definitely congruent. This one's just turned upside down. If you were to flip this one around, that's a terrible representation of flipping something around. I don't know why I drew that. If you took this shape and you flipped it like this, then it would be the same. It would be congruent with this. This one's is not congruent because they are not the same size. And then the last one you should have gotten congruent. Okay, those should have been your answers. Congruent is one of the easier topics in geometry. The next thing we're going to be talking about is similar shapes, and that makes it a little more difficult because the shapes look the same, but they have different measurements. Okay, let's talk about similar shapes. There is shapes that have similarity to each other. There is a relationship between their measurements. So think about anytime you ever cooked something, right? You might be making a recipe for something you make all the time, and now you got to make it for a party, so you're making it for a lot more people. You might double or triple that recipe, and what does that even mean when you say that, right? If I'm doubling the size of my cake, that means I need to take all the ingredients I'm putting in the cake and double them, right? Isn't that how it works? So that is actually a proportion, the proportion of 2 to 1, because the second cake is going to be twice the size of the first one. That means all the ingredients are going to be twice the size of the first one. A lot of times what we're looking for when we're talking about similar shapes is we're trying to use something called a proportional relationship to solve for the missing side, okay? If you look at the first problem here, we have a triangle and a smaller triangle. They are similar. Okay, now this is very important. The instructions have to tell you that they are similar. You have to be told that. You can never just assume that they are similar, okay? You have to be told they're similar. Each of these pairs of figures is similar, so find the missing side. That's what you're tasked with here, okay? On this problem, right, they look to be exactly the same, and so what we want to do is we want to relate the sides that are the same on the smaller and larger figure. So like for example, I'll use different highlighting colors for this. The 12 and the 3 side right here are in proportion to each other, and so I know that because I was told there are similar triangles, and therefore this side and this side are going to be in the same proportion. So what is that proportion, and how do I use that to find the missing side? So let's talk about how you set up a proportion, okay? First, we're going to talk about the values that we do know, okay? The smaller triangle side over the larger triangle side of what we know, okay? So smaller over larger equals smaller over larger. This is a proportion, okay? This side compared to this side is going to be the same proportion as this side compared to this side, okay? I'm sorry, this side compared to this side. As long as we're going in the same order, like this one then this one, means we have to do this one then this one. If we did it backwards, it would be this one then this one is equal to this one over this one, okay? Don't mess that up. So let's fill in the blanks here. We know that 3 is to 12, okay, because that's this one and this one. So that means that x, the side we don't know, it has to be also over the side we do know that goes along with it. Now we can solve this by doing something called cross multiplying. Whenever you have two fractions like this that are equal, this is a skill that you're going to use in many different things in algebra, not just similar shapes and figures in geometry. But when these are in proportion like this, let me change colors. How about green? You can multiply this one times this one, okay? And then that gets set equal to a color I didn't use that. How about pink? Equals this one times this one. That's cross multiplying, okay? So let's do it again. 3 times 20 equals x times 12. I couldn't put a second x there because that would be weird, so let me fix this. Instead of using an x over here, I'll use a dot. Boop. Okay. So you can solve this now very easily because you have a linear equation that you can solve. Okay, this is all something we covered in the last topic here. What you're going to do is simplify 3 times 20, which is 60, and this is equal to 12 times x. I want to get the x by itself, so I'm going to divide both sides by 12, and I get 5 equals x. What I have just solved for is this missing side. This side measures 5. It says the units weren't given, so that doesn't matter. But it measures 5 because it's in proportion. 3 is to 12 as 5 is to 20. Another way you can think about this without going through all this work is sometimes you can look at the numbers and just figure out what did I multiply 3 by to get 12, right? Let me cross off the line so you can see that. And we will re-highlight that side. Okay, What did I multiply 3 by to get 12? Well, I multiplied it by 4, okay? So 3 times what gives me 12? That's going to be the same thing as 5. No, I lied. That's going to be x. I'm sorry. That's going to be the same thing as the missing side times something gives me 20. Okay, that's another way to relate these. Well, 3 times 4 is 12, so x times 4 is going to give me 20. Well, what do you multiply by 4 to get 20? You multiply, bing, 5. You multiply 5 times 4 to get to 20. Okay, that was a lot. I want you to, right now, pause the video and do number 2, and just do number 2 for right now, okay? Because when you unpause, I'm going to step through the whole problem with you to see if you got all the steps right, and then I'm going to have you do 3 and 4 and just show you the answers. So pause your video and just do number 2. Do it all the way through, okay? And I'll be right back. Okay, did you have fun with that? So let's go ahead and solve this problem, right? So these look to be in the same like orientation already. Like this flat side is over to the side. This looks like the hypotenuse, perhaps, if this was a right triangle. I don't really know if it's a right triangle, but we're going to go with it, okay? This side is in proportion to this side, and this side is in proportion to this side, okay? So 1 over 3 is equal to x over 9. And now we're going to cross multiply, which means we're going to have 1 times 9 equals x times 3. Well, we can easily solve this as an algebraic expression now. This is going to be 9 equals 3x. And then you divide both sides by 3 to cancel that out. So x equals 3. That means this side right here is 3. Another way you could have solved this was you could have said 1 times something gives me 3, and x times the same something gives me 9. That's how proportions work, right? Well, this is easy to solve because 1 times 3 is 3. So this missing value has to be, whoa, that's the wrong symbol. The missing value has to be 3 because 1 times 3 gives me 3. That means the same missing value has to go here, okay? And 3 times something is 9. Well, what do you multiply 3 by to get 9? You multiply it by 3. And that's what we got in the other way, doing the other method as well. Okay, go ahead and pause your video and do 3 and 4. And when you unpause, I'm going to give you a few seconds here so you can pause it before the answers pop up, okay? But when you come back and you unpause, the answers will be there on the screen for you. So 3, 2, 1, pause. Okay, so this is what you should have gotten. You should have gotten 8 for this missing side, and you should have gotten 10 for this missing side. Except I just realized that I made an error. You're probably like, where's he getting 8 from? My bad. That should not be 8. The answer for this one should actually be, so this times 4 is this, and this times 4 is this. It's actually 2. 2 times 4 is 8. My bad. Sorry, you guys. This one's right, though. X equals 10. This side is 10 here. This triangle is essentially double the size of this one because all of the proportion of all the sides is doubled. 4 times 2 is 8. 5 times 2 is 10. If this was a right triangle, we could use the Pythagorean Theorem and find the missing side, and we'd probably, well, I don't think we'd find that it was doubled because that doesn't usually happen with Pythagorean Theorem, but it's not a right triangle because we weren't told that, and it doesn't matter anyway. So that is the conclusion to our notes here, was finding these similar figures, figuring out what the proportions were, and that brings this lesson to a close. I hope this was informative for you. The stuff we're going to work on for next week's lecture, the final lecture, the last class we have together, is going to be about graphing on a coordinate plane. How do you graph coordinate points? What's a y-intercept? What's a slope? That type of thing. And so I look forward to meeting with you guys one last time next week. And until then, please enjoy these notes in this video. There is going to be a Delta Math assignment that goes along with this if you want to do some practice and some real world examples. And don't forget to do your 3 hours of Essential Ed this week and complete this subject or this topic in Essential Ed. Okay, guys, until next time, I will see you later. Signing off. Bye-bye.